Welcome to this tutorial session of the European GNU Radio Days broadcast and recorded by Hervé Beuglet, Léo Cardoso, myself, Jean-Michel Fried, Gwen Goavet-Mirou, Thomas Lavarenne, and Cyril Morin. The way we've organized and envisioned these tutorials is as follows, as described on the European GNU Radio Days tutorial page. We've split the conference tutorials in two tracks, introductory and advanced. We aimed at synchronizing the schedule so that you might jump from one track to another, although we try to follow some story with increasing difficulty and acquiring knowledge throughout the successive tutorials. So on the introductory track, we assume little or no knowledge on GNU Radio, but we of course expect some knowledge on digital discrete time signal processing. And the first tutorial aims at showing how GNU Radio can be best used to prototype some of the concept of discrete time digital signal processing and having fun with real-time signal as opposed to GNU Octave, MATLAB, or post-processing with Python of recorded data sets. Léo Cardoso will continue on this track with receiving a real transmission with GNU Radio, and will show you how you can decode step-by-step a signal, an unknown signal using GNU Radio. So these two presentations are closely related to each other. After the lunch break, Léo will continue with a presentation of a cognitive radio framework, Cortex Lab, that was implemented in his laboratory at INSA Lyon in France. And for those registered with this presentation, you will be able to remotely access the various radio frequency front ends available through Cortex Lab. And finally, we will discuss some of the tips and tricks for efficiently using SDR in GNU Radio, following on the path introduced by Tom Rondeau, that GNU Radio might not provide all the facilities for decoding signals, but interfacing with external tools might be better suited. We will show how we can stream data that were handled at the radio frequency level by GNU Radio and piped to external tools, whether dedicated external tools such as Multimon or with general purpose post-processing tools through ZeroMQ. On the advanced track, we will start with Hervé's presentation on hacking IoT radio frequency communication. These are low bandwidth, low power consumption radio frequency communication systems for Internet of Things. And we will follow up with showing how we can introduce efficiently Python blocks within GNU Radio streams and nevertheless still keep the ability to graphically update GNU Radio companion flowcharts by including these Python scripts in Python modules and starting them with a Python snippet. So this will allow us to interact again with GNU Radio handling the low-level radio frequency stream and the higher-level data being handled by Python. In the afternoon, Gwen will show us how to run GNU Radio. I believe this is one of the most fascinating aspects of embedded electronic hardware, where GNU Radio will be running on these single-board computers such as the Raspberry Pi, and Gwen will show you how you can efficiently compile, cross-compile GNU Radio to run on these single-board computers. And finally, Cyril and Thomas will be discussing tags in GNU Radio for asynchronous processing and handling events in a GNU Radio flowchart. So again, all tutorials have been recorded, and the audience is expected to have completed their homework by having a quick look, at least a glance at the tutorials. Indeed, throughout these tutorials, the organizers and the speakers will be available for real-time discussions through various real-time chat systems. And we believe that this schedule would be best used by interacting and asking for complementary information on the broadcast tutorial that we had recorded. During this interaction, please favor chat communication over voice in order to avoid clutter and avoid having too many people talking simultaneously. And we will try to manage interactive discussion or having remote screen sharing when unsolvable issues arise. So enjoy the tutorials. have a great time and learn to better use these tools that we are going to show you during these presentations. Have fun.
Hello and welcome to this tutorial. My name is Hervé Beuglen. I'm a researcher at the XLIM laboratory at the University of Poitiers in France, and this tutorial is going to be about hacking an IoT chip with GNU Radio. To be able to do this tutorial, you will need two elements. The first one is the transmitter side. You'll need either an STM32 nuclear board plus an nRF24 module or a file that you can find on my GitHub. It's the file nrf_data.bin. For the receiver side, you will need either an USRP with the appropriate daughter board on the 2.4 GHz band or a cheaper add-on Bluetooth. If you go to the STM32 solution, that's what I'm going to do for this tutorial. You see here that I've got two boards. So the first board is an STM32 nuclear board with a daughter board equipped with an nRF24 module and also an OLED display to display the received room temperature. And you've got a second board which is the transmitter, and this transmitter is going to transmit the room temperature. It's an STM32 blue pill board. That's a really cheap board with an extension board I built especially for this. So it transmits the temperature, and as you can see, the room temperature is displaying on the OLED display. Of course, I've put all the code you need for these boards on the GitHub, but you have to know that to be able to modify the code yourself, you have to use the ST recommended tools. These are presented here. I use them quite often, and they are really nice and efficient tools. So the first one is the STM32CubeMX. It's a project generator. It allows you to configure the different peripherals you find on an STM32 and the pins, and also it allows you to configure the clock domain. At the end, it generates a project which is compatible to the IDE you want to work with, and one that's recommended by ST is the STM32Cube IDE that you see here, and you develop, of course, in C or C++ for these boards. So we are okay with the prerequisites. So let's see the expected outcomes. One thing, although we are not going to detail it during this tutorial, is that I suggest you to be able to convert an OOT module from GNU Radio 3.7 to GNU Radio 3.8. If you look at the internet, we see a lot of things in forums, people asking, well, I want to have this module in version 3.8. That's not so complicated to do. So I really suggest you to do it at least once, because it will help you to understand all the different elements that compose an OT GNU Radio module, and it's quite interesting. So I converted the OT module we're going to use for this tutorial to version 3.8, so I know what I am talking about. So on this part. So the second thing we're going to do is to create GRC blocks, and also we will modify quite a lot the C++ and Python code that we're going to find in the OOT module we are going to use. And finally, the third point that's really interesting to see, because it's really related to packet communication with GNU Radio, is the message passing interface and also the tags, which are elements that allows to synchronize with events. So that's also a nice feature. So the outline of this tutorial is presented here. We will first start with presenting some IoT 2.4 GHz low rate chips, and then we will see the GR Nordic OOT module on which we are going to work. It's been designed by Basti Research. Then we'll build an nRF24L01 Plus transceiver with GNU Radio. And finally, we'll go to a conclusion. So let's see the IoT 2.4 GHz low rate chips. So in fact, on the market, you find several solutions from different chip vendors, and most of these chips implement several RF protocols, and most of the time they've got proprietary protocols, so you cannot really exchange data from one chip to another, except if they use standardized protocols, which some of them use, like Zigbee or Bluetooth Low Energy. So they use packet communications with a rate of up to 2 megabits per second. And to deal with packets, they integrate a packet engine for packet handling, to construct the packet with the header, payload, etc. So here you see three examples. On the left, you've got ST Microelectronic S2LP, which is a quite low power chip, one of the lowest power on the market. And then you've got Silicon Labs also, which has quite a wide range of IoT chips, like this one, the SI4463, and of course Nordic Semiconductor with here the nRF52832, which allows you not only to use a proprietary protocol, but also Bluetooth low energy. So for this tutorial, we are going to use an old chip from Nordic Semiconductor. It's the nRF24L01 Plus, and is quite well known by embedded system guys. You find a lot of projects using Arduino with these chips, and the module, the complete module, can be found on Chinese sites for less than €1. Be careful, because most of the time these are not original chips, they are fake. The chip has been copied using an older integration technology, like this example shows it. So some of them are not as reliable as the original nRF chip. So you have to be careful about that. So what's inside an nRF24L01 Plus transceiver? Well, you will find, and it's the case for not only for this chip, but for most chips of this range. You've got the transmit part, the transmitter, including a power amplifier, and a modulator, a digital modulator. Most of the time it's FSK, or here Gaussian FSK, and also the RF chain with a low noise amplifier, plus the demodulator, of course. Then if you look at, that's the RF part. On the baseband part, you've got the so-called packet engine, and here it's the enhanced ShockBurst baseband engine. This chip communicates with a microcontroller or microprocessor using the SPI bus. So in summary, the main features of this chip is that it uses the 2.4 GHz ISM band, and you've got the possibility to select one channel over 126. It uses a GFSK modulation. The data rate can be varied between 200 kilobits per second to 2 megabits per second. The output power is also programmable from 0 to minus 18 dBm. So just an idea about the current consumption. At 0 dBm, you use 11.3 milliamps. It has got a quite nice sensitivity of minus 94 dBm at 200 kilobits per second, and the payload can go up to 32 bytes with automatic packet handling. And as I said before, it uses for the host interface a 4-pin SPI port, and the supply range is from 1.9 to 3.6 volts. So the proprietary protocol used by the chip is called the Enhanced ShockBurst protocol, and in fact it's just the way the packet is constructed. So it starts with a preamble, which is 1 byte long. It can be in hexadecimal OX55 or OXAA, depending on the fact that address starts with 0 or 1. Then you've got the address field, which can be 3 or 5 bytes. And then there's 9 bits with the packet control field. The packet control field includes the payload length, the packet ID, and 1 bit for acknowledging or not acknowledging the packet for the receiver. Then you've got the payload, which can vary from 1 to 32 bytes, and finally you've got also a CRC that is calculated from the data, which can be 1 or 2 bytes long. There are over NRF chips of this range. For example, the NRF24LU1 Plus, which integrates the NRF24L01 Plus, plus an USB full speed interface and a 8051 microcontroller. This is found in Microsoft and Logitech keyboards and mice. These two chips are not recommended for new designs by Nordic Semiconductor. And this is the type of dongle you see. We will talk about this dongle a bit later on. So now, if we look at Nordic range for this chip, you've got the NRF52 series, which has replaced the NRF24. In fact, it's a SoC, including the RF, like the chip we saw before, but also it includes the microcontroller, which is an ARM Cortex-M4. So there are several different chips in the range, as represented here in the table. These NRF52 can still use the Nordic proprietary protocol, which is the NS ShockBurst. And the development boards are really affordable, because for this development kit, as shown on the photo, you will only pay 40 euros. So where do we find NRF chips? Well, in a lot of Microsoft and Logitech wireless keyboards and mice. Also drone remote controllers, like the one you see here on the slide, sport watches, bike equipment, heart rate monitors, and things like that. Well, so it's a really well-known technology, quite old already, and so you'll find lots of resources about hacks for mice, drones, etc. It uses packet communication, so it's quite interesting to fiddle with it using GNU Radio. So that's why we have the goal of this tutorial, which is to build a Nordic NH ShockBurst compliant transceiver with GNU Radio. So at the end, we'll be able to mimic the NRF24 chip with GNU Radio. So either for the transmitter you use an STM32 nuclear board with the NRF24 breakout board, or you can use the file I was talking before, the nrf_data.bin. So let's have a look about the outer three module we are going to work on. So the first question when you start with this project is, do we have to start from nothing? Of course, the answer most of the time is no, but in fact there are not so many up-to-date implementations to deal with these IoT chips. Some of them use the old message queue way of packet transmission, like the GRCC1111. So I came up with the GR Nordic 03 module from Bastille Research, which uses the GNU Radio message passing interface, and it's been designed to identify vulnerabilities of wireless keyboards and mice. And this work has been presented at DEF CON 24 in 2016. So the only work we have to do is to convert it to version 3.8 of GNU Radio. So the work presented at DEF CON 24 was mouse jack injecting keystrokes into a wireless mice. So presented by Mark Newlin from Bastille Research. So in fact, mouse or keyboards, they've analyzed for this work the wireless mice and keyboards from 16 vendors, looking at proprietary protocols and 4 families of transceivers, and then they found 16 vulnerabilities with keystroke sniffing, keystroke injection, and some of them were just unpatchable. And just a quotation from Logitech in 2009, since the displacement of a mouse would not give any useful information to a hacker, the mouse reports are not encrypted. So well, we can think that okay for a mouse, but as you know, most of the time you've got on the same RF system, you've got the mouse and the keyboard. So the peripherals, these two peripherals, send the information to a dongle, the dongle we saw before. And this dongle, which is USB HID, it sends the user input to the computer. So in fact, an attacker can talk to your dongle, that's possible, with keystroke injection, represented here, or simply eavesdrop on your unencrypted keyboard. Okay, so since the keyboard is not your keyboard data is not encrypted, you can get, for example, simply a password of someone. If you want to know more about these different attacks they've tested, you've got the link I've put here on this slide. So now let's go with building an NRF24L01 Plus transceiver with GNU Radio, and it's the part 1 of this tutorial. So let's go discover GR Nordic. So as I said before, it's been created by Bastille Research and it's available on GitHub. However, there are no updates since September 2016. So it's still on GNU Radio version 3.7. So I forked this module and updated it to GNU Radio 3.8, and so you will find it on my GitHub. So you've got, in fact, two branches, version 3.7 and master, which is 3.8, and also a third one, you have to say, is the tutorial one that you can use for the tutorial. So just a few words about the conversion procedure from 3.7 to 3.8. This is documented in on the GNU Radio wiki, as you've got the link on this slide. But I can tell you a few words about that. So when you are going to do a conversion like that, what is recommended by GNU Radio, by the GNU Radio community, is to use, in fact, gr_mod tool. Gr_mod tool, in fact, is going to do all the tricky work about dependencies on the different tools like Swig, etc., to the right version. So what you do is simply you start with the same name, you create the module, and you add the different blocks using gr_mod tool. And this is working quite well. I tried it, so it worked. But there's a second problem that's for me was a bit more tricky, is the fact that between the version 3.7 and 3.8 of GNU Radio, you've got a major change in the Python version. You go from Python 2.7 to Python 3.8, and a lot of libraries, Python libraries, have changed their names. Some functions have been renamed, so it can be really tricky, and it takes quite a certain time to go for the change. But anyway, I really advise you to do it at least once, because it's really interesting in the fact that it will give you all the important elements you have to know when you design an OOT module, the way it is architectured and the way the blocks are communicating together and things like that. So try to do it at least once. So quite easy. If you want to start with GR Nordic, you just go and clone the repository. So you can check out between the three different branches represented here in red, according to the version you want to work on it. Then, of course, you create the build directory. You go into this directory, then you go with cmake. You go for a make, and don't forget to add the option -j with the number of threads your computer can handle, because this is going to be really a gain in time. Then you go with a sudo make install and a sudo ld config. So if we go now into the GR Nordic directory, and precisely in the subdirectory lib, we'll find in fact two blocks. The first one is Nordic_tx, Nordic_tx. And what's interesting for us, because we would like to create two GRC blocks, is to see the type and the size of the input and the output of the block. So what we can see from the private constructor, which is represented here, is that the input is a Nordic tap_in message. So it uses the message interface, the GNU Radio message interface, with PMTs that we'll see afterwards. And the output is going to be a stream of unsigned int 8. So that's interesting for Nordic TX, and we've got also a block called Nordic_RX, which is the receiver. So the input is going to be a string of unsigned int 8. So the output is going to be a message using the message port interface of GNU Radio. So to use these blocks in GSRC, you can just notice that in fact they have not been implemented, because the guys from Basti research used simply Python scripts, and they didn't really care about GNU Radio companion blocks. So what we would like to do now is to add these two blocks, which will use the YAML format. So we will have to create these two blocks and verify afterwards, of course, that this implementation works in GNU Radio Companion, so that you can see the blocks. To build a receiver with GR Nordic, starting with, of course, a transmitter, which is either the STM32 board fitted with a NRF24 module, or a file containing the recorded ESB packets. We need to know what's going to be inside the packet, in fact, and it's represented here in this table. So the address length is going to be 5 bytes, and it's going to be OXE7 repeated 5 times. The payload size is going to be 8 bytes. The temperature is going to be the payload, and it's going to be represented in this format, xx.x. The CRC is going to be 2 bytes, and the data rate is going to be 2 megabits per second. And to avoid the fact that we could have jamming because of the Wi-Fi devices, I use the RF channel 120, which gives a frequency, carrier frequency of 2.52 gigahertz. So let us first have a try with the existing Python example. In the subdirectory example, you will find a file called nordic_receiver.py. It's a Python file, and as you can see, it implements a receiver. So we see that the SDR source for the receiver is Osmo SDR. All the hardware which are compatible with Osmo SDR implementation will work, but it's not going to work with the add-on Pluto. So we'll see that afterwards. And so on the left, you've got the parts dealing with the SDR source, and after that, on the right, you've got the receive chain with the different blocks which are connected to be able to receive the NRF24 data. So GR Nordic is said to be SDR agnostic. Of course, it's compatible with a lot of hardware which uses GR Osmo SDR, but since it doesn't work with the add-on Pluto, I will ask you to modify Nordic receiver .py accordingly, and also to study Nordic receiver file to identify the relevant blocks and their connection, because by doing so we'll be able to find the right blocks after that to build a Flowgraph in GNU Radio Companion. So you will also see in this Nordic receiver file that there's a function implemented called Nordic Tap Printer. So Nordic Tap Printer, to be concise, just does something important. It converts the so-called PMTs, so polymorphic types, in character, in strings that are then printed on the screen. So this is a function, a block. It can become a block, in fact, and we would like that it becomes a block that we could use in GNU Radio Companion. So that's the third thing I'll ask you for this first part of the tutorial, is to integrate the Nordic Tap Printer block in GR Nordic explicitly. So you will have to create a Python file called nordicblocks.py and copy the code of Nordic Tap Printer found in Nordic Receiver file. Okay, so you add then Nordic blocks to the module by modifying the CMake lists file .txt and also init_dot.py. Then you create a grc YAML file for the new Nordic Tap Printer block, and of course after doing all these manipulations you will have to rebuild the module. Final thing I'll ask you to do for this first part of the tutorial, and I'll let you some time to do that, is to create a GRC Nordic Receiver flow graph. So now we are going really to the GNU Radio Companion part. Using the new blocks and the appropriate GNU Radio blocks, you'll have to design a GRC flow graph receiver. So it will visualize the incoming packets, and I advise you to add a power squelch block and synchronize the time sync block with the squelch and underscore SOB tag. So set the threshold to the detection threshold to -35 dB. Also study the GFSK.py, which is located in the GNU Radio installation part of Python. The path is indicated here, and in particular the GFSK mode here block. So I would like you to expose the block that compose this GFSK underscore mode. So okay, it's your turn. It's time to work. I will let you some time to work. So I've just summarized on this slide the 4 tasks you will have to work on, and you can interact with me using the chat link which will be given during the conference. So don't hesitate if you've got a problem to ask me. I'll answer in real time. See you in a few minutes. Welcome back. I hope that everything went fine. Let's see the expected results. So the first thing is to get accustomed to the YOML language, yet another markup language. Well, it's quite easy. As you can see, the tags are really clear to understand. The first thing is the make keyword, where you just have to look at the constructor you find in the .cc corresponding file. So here we've got a variable called channel count. So it's a parameter and you have to define its type. So then you have to add the inputs and the outputs, and you have to precise the domain they work on, and also if you use a stream you have to define the type. So here it's bytes. So it's the same for the Nordic RX block .yml with the different variables and parameters and the inputs and the outputs. So let's see now the modification and the blocks we find in the file nordic_receiver.py. So the first thing to do if you want to use the Pluto is to import the IIO library and use this line where you define the sample rate, the RF frequency, etc. So you've got different parameters which are detailed in the documentation of the Pluto. Then if you look at the connection, you see that the Pluto source is at the beginning of the graph. Then it is followed by a low pass filter, and this low pass filter is then followed by a GFSK demodulator, and then we go to Nordic RX underscore RX, sorry, and finally a Nordic tab printer. So we've got all the blocks we need to build the flow graph in GNU Radio Companion. So it gives you a receiver like this one, and let's see now how this flow graph works with the hardware. So if we look at nordic_receiver.py, I'm going to use it to listen to the channel 120, and I'm going to switch on my transmitter, which is the STM32, which is transmitting the room temperature. So I start here and I see the packets, and it works pretty well. So of course I've got my Pluto, which is connected on my USB, and you can see that it works pretty fine. Let's stop it and go to GNU Radio Companion. So if you look at the receiver flow graph, so you've got your Pluto at the input, and then I've added a power squelch block with a threshold of -35 dB, so it's only going to trigger the receiving chain when the level the Pluto gets is over a certain level. So the sample rate is 4 mega samples per second. We've got a low pass filter to filter the input to have less noise, and then normally you just use a GFSK demod block, which is here disabled because I just wanted to, since it's a here block, I wanted to a hierarchical block. I wanted to see what was inside. So I saw in a gfsk.py file that you had 3 blocks. In fact, the quadrature demodulator, which performs the frequency demodulation, and then you've got a clock recovery block using the Müller and Müller algorithm, and then the binary slicer. A binary slicer is just looks at the input when the level is over 0. It says it gives a 1, otherwise it gives a 0. So at the input of the binary slicer, you've got simply bits. That's what we are going to see when we launch the Flowgraph. Then of course we've got our Nordic RX block with the same parameters as the transmitter, and we have got the output of this block going to the Nordic tap printer block we've just designed. If you look in the category on the right, you see that in Nordic you've got Nordic RX, Nordic TX, Nordic tap printer, and another one that we'll see afterwards. So I wanted to synchronize with the bits coming from the packets. So I used a correlate access code block, which correlates with the header of the NRF24 packets. So shows the results on a time sync. So let's see if this works. Okay, it works pretty fine, as you can see. So we see on the figure that we see the packets with the header and then the data, and in the second graph we see the bits, the resulting bits after demodulation. So it's working really fine. Okay, let's carry on with part 2. So let's give a few words about GFSK modulation. So this is defined by this equation where you see that we've got a cosine with a carrier and a phase that's varies with the data we want to transmit. So E is the bit energy, T is the symbol duration, and FC is the carrier frequency. So transmitted information is contained in the phase, the angle term. So phi is given by this equation here, where alpha I is the message signal, which is here +1, -1, representing 1 and zeros. So we transmit binary data, so there are only two possibilities. So Q of t is describes the shape of the phase transition, whose magnitude is proportional to the modulation index h. So h is given by the difference between the frequency representing the transmission of A1 and f0 representing the transmission of A0. So it's equal to 2 multiplied by fd by t, where fd is simply the difference between the frequency representing the f1 minus the carrier frequency, which is also equal to the carrier frequency minus the frequency representing the f0. So now after that we do some pulse shaping, and that's why FSK is transformed into GFSK. As you can see, it allows to get rid of side lobes on the spectrum, so you've got a much cleaner spectrum. That's the advantage of the Gaussian filter. This Gaussian filter is given, the impulse response of this filter is given by the equation represented on the top of the slide. B is the filter's -3 dB bandwidth, and in fact for GFSK it can be characterized by the BT product. For example, in Bluetooth, using this Gaussian FSK, BT is equal to 0.5. And here you've got an example of the shape you get after passing the Gaussian filter for the data, binary data represented by the string at the top of the figure. So to build a GFSK modulator implies to implement several operations. So the first thing, when you've got bits represented by 1 and 0, you transform them in +1, -1. Then you add the pulse shaping by you just apply a convolution between the data and the filter impulse response. You multiply them by 2 by pi h, then you integrate, then you get, of course, the phase, and this you apply to an IQ modulator represented here with the upper branch, which is the cosine part, and the lower branch is the sine, the sine branch. So you multiply, of course, by the carrier, and you obtain, after summing these two branches, you obtain the GFSK signal. So it's quite interesting to have a look in gfsk.py to see how it is done in GNU Radio, because some operations you see here are analog operations, and you have to implement them digitally. So there are some tricks about that, and it's quite interesting to study it. So for the demodulator, most of the time, it's not the only way to do it, but we use a phase shift discriminator represented here. Again, the multiply block you see just the carrier, which is cosine or sine when you apply a phase of pi divided by 2. So the two signals Si of t and Sq of t are given by the equations at the end of the slide. And what you have to do after that is apply a low pass filter and apply an arc tangent operation to get the phase. And if you use a differentiation operation, you get the message at the end. So it's interesting to see also how it's done digitally by looking at the same file I was mentioning before, gfsk.py, to see how it is done in GNU Radio. Looks something like the diagram you've got at the end of the slide. Something a bit different now is something that's working behind the scene. It's when you launch a reception of when using this OOT module, there's also something that produces a UDP stream, and it's been implemented in Nordic_RX.cc, and it uses the Boost library just to send the data decoded to a UDP port, which is 9451, and you can use the network tool Wireshark to visualize the packets that you decode. So it's quite interesting, because Wireshark allows you to see a lot of things when you want to analyze network protocols. So they've implemented that. So I've just give you here the command you have to use if you want to decode the Nordic packets, ESB packets with Wireshark. You have to use a Lua script, which is located in the Wireshark subdirectory in GR Nordic. So now let's have a look on the GNU Radio message passing interface and the strange things called PMTs, polymorphic types. In the case of packet transmission, we're not really interested in data streaming, and that's the usual way of working for GNU Radio. So we would like to transmit asynchronous messages. In GNU Radio, there are two mechanisms to pass messages: synchronously to a data stream using stream tags, or asynchronously using the message passing interface. From a programming perspective, a message can be represented as a data type. In Python, this is not really a problem since it is weakly typed. C++, on the other hand, is strongly typed, and it's not possible to create a variable without knowing its type. So in GNU Radio, we need to exchange the same data objects between Python and C++. So we use polymorphic types, or PMTs. Hence, messages are PMTs and can contain anything, commonly vectors of bytes for PDUs, that's quite common, or a dictionary with a key value pair. You need to understand a minimum how PMTs work in GNU Radio, and you can have a look on the wiki where there's a page dedicated to them, and it explains quite well how they work in GNU Radio. So now we would like to build a transmitter. We've got already a receiver that works. So now the transmitter, the Nordic transmitter block, which already exists, it requires a message input block. This message has to be a PMT, and the PMT will be made up of these fields. So channel index, channel, data rate, etc. So we will use these fields. We would like to send this packet every 0.5 seconds, exactly the same way as with the STM32 and the NRF24L01 plus breakout board. So to build this transmitter, to validate the transmitter chain, I'll ask you for this is your first job in the second part of this tutorial, is to build a TX-RX loop model with GNU Radio Companion. So some tips to help you. Use a message strobe block as input to the Nordic TX block, and take care of how to write the PMT and the conversion from a string to a PMT. So you can have a look at line 79 of Nordic _TX _EMPL.cc. So if you validate this step, you will see that your model, although it's complete, doesn't work. It doesn't work because there's a bug in Nordic _TX _EMPL.cc. So find this bug, which it's quite obvious, it's so stupid, but well. So after this bug, it's working, okay. It's supposed to work. So let's build a transmitter model. You can check this model with either an STM32 nuclear board plus the NRF24L01 plus module, or with a second Adam Pluto in receive mode if you want. Then we play a little bit. That's the second task I ask you to work on, is to add a length tag to the Nordic TX block, and this can be useful to synchronize visualization blocks So what you have to do is simply to edit the .cc file for Nordic TX and add a tag named packet length, whose value is the length of the produced packets. You can have a look on the GNU Radio wiki to help you on how to add tag to a block. You have to be careful about the packet length, which should increase because of the bytes to bits conversion and the upsampling rate. So how can we do that? That's a good question, and you'll have to think about it. So get, build and install GRFoo. That's our first solution. GRFoo is a Note of 3 module that's been designed by Bastian Blossel, and you will find something nice which will avoid you to go and add your tag in the .cc file, because it's got a block called burst tagger, and it adds automatically a tag in the stream so that you don't have to edit anything. So it's quite nice. But another solution is also to add manually start of block and end of block tags directly in the Nordic tx.cc without using GRFoo. You've got several solutions, so you can try one of them or all if you have time. And finally, we'd like to create our Nordic tap transmitter block. This will allow us to directly enter text into this block without having to fiddle with all the PMT's conversion functions. So a part of this block is in the file nordic_channelized_transmitter.py. It doesn't meet our needs for GNU Radio Companion because there is no associated YOML block. So you have to create the associated YOML block for this block as well. So you can write this block and add it to our file nordic_blocks.py. It's a way to put all the block in one file. It's a neat way of organizing our code. So you can finally add your block to the GRC transmitter model you've built before and check that everything works. So now it's your turn. You've got some time to address these 4 different tasks, and we'll see. We'll meet again in a few minutes. Welcome back. I hope that everything went fine. Let's have a look on the expected results. So here are my models for the different validation points. So the first one is the RX-TX loop, and the second one is the transmitter with a message strobe block. Here you've got validation 7, where I have added a burst tagger block with installing the GRFU OOT module. And finally, the Nordic tap transmitter block added to the transmitter. Let's have a look on how these all these models work by using GNU Radio Companion. So let's see the first model, which is TX-RX loop. So we just have added, in fact, the different block. We do a loop with Nordic TX, Nordic RX, and Nordic tap printer. So let's see if this works. Yes, as you can see, I've also added the packet length tag and the TX start of block and TX end of block tags in the transmitter code, and you can see that of course the packets are correctly decoded, as you can see with the text here. Okay, so it's quite nice to have a synchronization because you see exactly what happens with the packet with the different tags we use here. Then I'll start with the first transmitter solution. So in fact we use a Pluto as a transmitter. We use a GFSK modulator, and of course our Nordic TX, which starts with a message strobe. So you have to be really careful about the way you build the PMT. In fact, here, if you edit this block, you see that you have to use the function which is pmt.init_u8 vector, where you have to indicate the size of your vector and the name of the vector. So packet vector is just given here by this. It's a concatenation of two strings, in fact, where address is of course all the fields we need to build the packet. The payload is just the temperature here, which is 22.75. So let's start the Flowgraph to see if everything works. So we are transmitting here, and we have to see if it's correctly received by our STM32. You can see that the temperature is 22.75, and that's correct. And if I reset, when I reset, you can see that it's no longer working, and we will see why you've got this problem. In fact, the packet has apparently been received only once by the receiver. So let's see now the third model, where we have just added the packet length burst tagger, which is our GR-foo block. Okay, so you have to be careful about the symbol rate and the sample rate to have exactly the right length for this. So let's go and launch also, and as we can see again, we get 22.75. so this seems to be okay. And again, it's received only once, so there seems to be a problem that we have not taken into account. Let us now see the final block, the final flow graph, sorry. And this final flow graph is complete with all the different blocks we've designed, and we are going to send a message with the temperature, which this time is going to be 24.75, and we send it to our STM32 receiver. Let's go and launch this model. Okay, so let's have a look on the STM32, 24.25. That's the right temperature we see here. Okay, so this seems to work fine. So now what we can see is that for that model, the temperature is always displayed and it doesn't work only once. So what is the reason of this behavior? That's what we are going to see now. So sometimes the packet is received, sometimes it is not. Can you find why? The answer is simply in the NIF24L01 Plus datasheet. Is simply because of the PID field. So the PID field is used to detect if the received packet is new or retransmitted. So PID prevents the PRX device from presenting the same payload more than once to the receiving host MCU. The PID field is incremented at the TX side for each new packet received through the SPI. So in fact, the code that we found for Nordic TX doesn't do that. So we have to think about incrementing this packet ID. So you just have to modify the Nordic tap transmitter block accordingly. So here are two red arrows to show where you have to do this modification. So you just increment modulo 4 this packet ID, and then everything is going to work fine and as a real NIF24 chip transmitter. So I give you some homework, something really fine to do with this OOT module that you can add is to build a BLE advertiser with GR Nordic blocks. So in fact you are limited to 32 bytes, but this allows to simply broadcast temperature to a BLE in advertising mode. So it's possible to do that, but you have to encode the data so that it's compatible with the BLE standard. So that's a quite nice homework if you want to try it. So now let's go to a conclusion. So in fact my background is electronics engineering, and I'm not a computer guy. So in fact GNU Radio is something that mixes computer science and also something related to electronics, digital electronics. So it's quite nice to have a tool like that, to have insight in radio frequency electronic devices. And the system allows you also to deal with packet communication, although it's a bit more complicated. There are several out of 3 implementations available for packet communication, burst communication. There were GRBurst or GR event stream by Team Oshi, but it's no longer maintained. So the successor are the OOTs from Sandia Labs, for example, GR-PD utils and GLDR timing utils, and these are quite nice to deal with packets. So think also about one thing important. GR Nordic, we played a lot with it. It's upgradable quite easily to all type of IoT chips. I could have used a chip from ST. I just had to adapt the packet engine part. So there's a code called NN ShockBurst packet. You just have to change this code, and the rest of the code, the TX and the RX, is about the same. So it's quite easy to implement other type of IoT chips. Here are some references that will give you some interesting details about some points we have seen in this tutorial. I thank you very much for your attention, and I hope that this tutorial you enjoyed it. Thank you very much.
Welcome to this advanced tutorial on GNU Radio and GNU Radio Companion and how to make it interact with Python, the underlying language generated by GNU Radio Companion when executing a flowchart. I am Jean-Michel Fried and will be hosting this tutorial for the next hour and a half. The outline of the presentation is as follows. This tutorial aims at emphasizing communication between GNU Radio Companion and external software by streaming data from GNU Radio Companion through ZeroMQ publish and configuring the parameters of the GNU Radio flowchart by a server running in a separate thread. The conclusion of this presentation will emphasize application to synthetic aperture radar realization. So what is the problem statement we wish to address? Some SDR processing might be best performed outside of GNU Radio. Indeed, GNU Radio scheduler will feed successive processing blocks from source to sink with a continuous stream of data, and usually losing data is frowned upon. On the other hand, some processing might best be performed in burst. For example, we will address radar systems, but also digital communication might lead to processing bursts of data when communication starts and might not require continuous streams. So in this example, we wish to make GNU Radio and GNU Radio Companion interact with external processing tools, whether C, C++, or in our case, GNU Octave, the free open source implementation of the MATLAB language. Furthermore, we might wish to interact with the GNU Radio parameters in some discrete manner. For example, in the case of synthetic aperture radar, we might wish to move sometimes the antenna while leaving the data stream continuous, for example, because some phase alignment has been initialized and any stopping the continuous data stream might lose this phase calibration. So these two interactions from the radio frequency front-end continuously streaming data to GNU Radio and then later feeding some external software for punctual processing, Python, C++, GNU Octave, and this external tool providing commands and parameters to GNU Radio will be the outline of this presentation. So let's consider a very simple flow graph where we have, let's say, for example, a noise source feeding a low-pass filter, and we wish, for example, to have some external tool interacting with the data stream. So we create a low-pass filter with its parameters, and because there is no hardware data rate limiting peripheral in this example, we need to throttle the data stream before feeding the spectrum analyzer. So in this example here, very simple flowchart that we will call demo 1, for example, we store this into a temporary directory. And when we execute this flow graph, surely enough, we get the transfer function of the filter that we just created. Now, let us consider how we could interact with this data stream. What we see here is that the program that was generated by GNU Radio Companion will create the various blocks. For example, we have here the creation of the sampling rate variable. We have here the spectrum analyzer creation with its various parameters. And we have, in this example, the throttle block with the throttle block and the low-pass filter that have been created. Now, once these various blocks have been created, we connect them between each other. And once these connections have been completed, we will have the top block start until the user stops the execution and completes the execution of the flowchart. We might have some parameters that will be changed dynamically by the user, and these are callback functions if, for example, we create a variable f and this f variable is used to define the source block, the low-pass filter cutoff frequency. In this example here, what we will see is that the variable can be dynamically modified by the user. And if we now look at this f function that we just created, we have the variable f, and we might get the current value of a variable, and we might set the current value of a variable. So the general outline of a GNU Radio flowchart, GNU Radio companion flowchart output, the Python script that has been generated, will never give us access to the actual IQ data. The IQ data stream is handled by these various processing blocks, and these various processing blocks are connected between each other, but there is no way for us from this Python script to interact with the data. Hence, our interest in streaming the data to an external tool. Nevertheless, we might want this external tool to be able to interact with the parameters, in this example, this variable f that we just created. So we might wish to have this external tool interact with getF or setF for getting and setting the variable values. So that tells us how we wish to write our external processing functions. And finally, because we see here that the main function from GNU Radio Companion starts the execution of the Qt framework until it stops, we need to have some way of interacting with this scheduler from external tools. So if we come back here to the outline of the presentation, this is again, we have this class that has been created with its main function that will be executed, various callback functions, the block instantiation and connections. And we need to interact with these self-generated Python programs in order to introduce our own functions. So Marcus Müller's answer to this question was to use the Python module and Python snippet, which is the topic of this presentation. So first of all, these callback functions are actually created whenever a block is defined. In this example, for the GNU Radio Companion block description of the GR-RPI TX that we present at the European GNU Radio Days presentations. In this example here, the radio frequency source accepts two parameters, the sample rate and the carrier frequency, and we wish to allow the user to dynamically change this carrier frequency by creating this parameter. So this parameter sample rate is only provided at creation of a block, but this carrier frequency here might be changed in a callback function which is called setFreq. So the C++ implementation of this block will provide this callback function that will change the hardware parameterization of the Raspberry Pi transmitter by feeding this new carrier frequency variable that has been provided by the user. So in this example, we might wish to have an external parameterization of this carrier frequency, for example, for a TCP/IP server that will send commands to the Python processing block and allow for this callback function to be called. So we have an external Python client that will connect to the Python server that will be launched upon execution of the GNU Radio Companion flowchart, and this server will receive the command which will call the callback function, which will then reach the C++ implementation of the callback function to change the hardware parameterization of peripheral. And finally, because this server will have to be launched somehow, we will need the Python snippet to execute the thread and providing the self argument to allow tuning the parameters of the Python program that has been generated by GNU Radio Companion. So let's try to do this step by step. Here is an example of streaming the data from GNU Radio to an external piece of software. And in this example, we will consider GNU Octave with its ZeroMQ implementations. So we have here two sources that will be displayed on the queued graphical interface frequency sink, which is the spectrum analyzer. And because we want to make sure that these two interleaved data streams are sampled at the same time, we create this unique stream, which is the two data sets interleaved here. And we wish to make sure that we know the amount of data that is transferred from GNU Radio Companion to the external piece of software. So we convert these stream to vectors of known size. And thanks to this, we will use the ZeroMQ publish sync, which is actually a UDP-like communication where data are continuously streamed. If there is no receiver, the data are just lost, and the data stream will keep on flowing, which is the requirement that we wanted to meet for example, prevent losing the phase calibration at initialization. And if some external software collects the data, then it will be able to process this data. ZeroMQ is an advanced framework on top of IP and TCP or UDP that will create data packets more advanced than what TCP or UDP would allow, and will provide tags so that some receiver might only process a subset of the data that are being streamed. So if we look into GNU Radio Companion, we will find the various ZeroMQ publish, subscribe, which is the UDP-like, and we will find some of the other methods provided by ZeroMQ in GNU Radio Companion. So in this example, we will use the ZeroMQ publish, subscribe, UDP-like framework, where we provide vector length data, which has been created by this stream to vector. We will mention that we communicate with a local host, 127.0.0.1, on a selected port 5555 over a TCP link. And on the other hand, we will have an Octave script. In this case, it will be this very simple script where we load the ZeroMQ package. We define a sampling frequency which has to be consistent with a sampling frequency that we define here in GNU Radio Companion. In this case, it's only used to display the x-axis of the Fourier transform of this data. So we create this linearly spaced x-axis for the display of the spectra. And we must make sure that the number of samples that is being received here is consistent with the number of samples that is transferred by the ZeroMQ sync. So what we wish to demonstrate here is how we open a ZeroMQ socket in the subscribe complement to the publish sync. We mentioned that this socket is connecting to the local host on the port 5555. If you were to run this flowchart on a remote computer, then you would mention here that this address would be the remote IP that is exposed to the communication interface, and this would be as well the remote server address. We mentioned that this socket is a subscribe, and we will collect ZeroMQ receive the NT data, and because these are bytes, we must remember that we have here interleaved data, so each data stream is 4 bytes, so that we interleave these 8 bytes data stream, and because these are complex numbers, we must remember to multiply by 2. So here we collect NT times 8 times 2 bytes, and because this is small enough, this will be received in a single burst. We might wish to check if we have larger bursts that the total number of data has been actually been collected, and then we convert these bytes that have been received from the ZeroMQ socket into single complex values to be processed by Octave. Once the vector length data has been collected, we split the interleaved data stream into channel 1 and channel 2, and we finally plot the spectra. Now, one of the issues is that we wish to process this continuous data stream. GNU Radio Companion will be streaming continuously data, and here we wish to collect bursts of data. In this example, NT equals 2048 samples. And the challenge is that if we're not careful, we might collect old data that have been piped a long time ago. In the case of radar systems, we want to make sure to collect data when the antenna is at a fixed position in a known azimuth. And to do this, the best way we found is to close the socket and open it just before we collect the data. We did not find how to reset the stream and make sure that the currently collected data are the latest that have been streamed by GNU Radio Companion. So the easiest is to close the socket and open it just before collecting the data. So if we run this example, we see here that by running the example, we get these spectra of the two data streams that are being generated by GNU Radio Companion at a local frequency and local frequency times 1.6. And if we move a frequency shortly enough, these two spectra are moving in real time. Now, if we run simultaneously the Octave script here, so by running Octave and calling the program name here, we simultaneously get these spectra. And if we move the spectrum in GNU Radio Companion, we see that indeed Octave is simultaneously streaming the data and displaying the correct spectrum, demonstrating that we have received the latest data. If we now stop the Octave script, we see that even though the Octave script has stopped, GNU Radio Companion keeps on running, as opposed to a TCP communication that would stop the execution of the server until a new client connects. And if we move again the spectrum and restart the Octave program, we see that indeed the latest data are being displayed with the new spectrum position. So this demonstrates communication from GNU Radio Companion to an external piece of software that might process bursts of data and not necessarily continuously acquire data and maybe throw away a lot of this information. In the case of radar systems, you might stream several tenths of megabyte per second. You only want to collect the data when the antenna is in known position, and this will best be done by this Octave script running the whenever valid bursts of data are available. Now, we might want to demonstrate this in a practical demonstration other than just displaying the spectrum. So let's try to see how we can run this example on a correlation where we have a signal source. In the case of a radar system, that might be a noise source or whatever broad spectrum source, which might also be pulses. And we will simulate a target by introducing a delay between a reference channel and the measurement channel. So this might be, for example, targets at different ranges from the source. Again, because we want to make sure that the reference signal and the delayed targets are sampled at the same time, we interleave this data stream as we've just seen, throttle block because there is no hardware data rate limiting peripheral in this flowchart, and collect burst of data. So in this example, the ZeroMQ script will not display the spectra because the spectrum of a white noise would be a flat spectrum, but we will display the cross correlation between vector 1 and vector 2. So if we run this example, here we execute, we see here the two streams, the reference signal and the time delay signal. And if I were to introduce some delay between the reference and the measurement, you would be hard pressed to detect these time delays from the raw data. So if we run this using the Octave script, so the Octave script is as follows. We start by loading ZeroMQ, and we will need the signal processing toolbox to run the cross correlation. Again, we define the sampling frequency and the number of data transferred from the server to the client. And in this example, we make sure to clear the vector that will be fetched to make sure that we get the latest data. We close the socket after collecting the data, and we open it over here to make sure that we get the latest information, connect to localhost port 5555 again, and in a ZeroMQ subscribe, get the single value complex as we did before, except that now, instead of plotting the spectra, we plot the cross correlation between these two vectors. So here is the result of this execution. What we see here is the spectra updated every about 200 milliseconds, and if I am to move the time delay, we see that indeed the cross correlation is updated continuously. Now, GNU Radio Companion will of course not allow you to introduce negative delays because it couldn't know what was the output in the past, so you only have positive delay, and we start at 2048. The cross correlation is twice the data set, and we move to the right here. So what we see here is how we can efficiently use external software with the cross correlation of Octave in this case for running the cross correlation. We might wish to compare the data generated by Octave with the data generated by GNU Radio Companion. Now, here is an example of running the cross correlation in GNU Radio Companion. If we have a quick look at the slides, the demonstration of this system was discussed at the GNU Radio conference in 2020. So here is the example of a cross correlation implemented in GNU Radio Companion. If you remember your convolution theorem, the convolution theorem tells you that the Fourier transform of a convolution between two signals is the product of the Fourier transforms, and the difference between a convolution and a correlation is that the convolution is the integral of the first signal times the time flipped copy of the second signal, as opposed to correlation, which is the integral of the first signal times the time delayed copy of the second signal. So between a convolution and a correlation, we have a complex conjugate to flip time, and this is exactly what we're doing here. We take the Fourier transform of the time delayed signal, which we convert from a stream to a vector because the Fourier transform can only operate on a fixed size vector. we take the original signal and take, again, the Fourier transform of the signal to multiply conjugate. So we take the complex conjugate of one signal with respect to the other and take the inverse Fourier transform before going back from a vector to a stream and feed acute time sink. So if we run this example here, we have the estimate of a cross correlation as performed by GNU Radio companion. And if I move here the slider, we see again in the time domain it will be very challenging to detect this time offset between the reference and the measurement signal, but the correlation nicely shows how this correlation shifts. And if we compare this with the output of cross correlation of GNU Octave, we have this consistent behavior of a cross correlation peak, obviously. So in this example, we can reach the result using GNU Radio Companion, except that GNU Radio Companion will process a continuous data stream, whereas if we are steering an antenna, we might wish to only process bursts of data in a known condition, and GNU Octave would be best suited to this operation. Indeed, if we stop GNU Octave from running, GNU Radio Companion will keep on processing the data as expected. So this concludes the demonstration of streaming data from GNU Radio to an external tool, in this example Octave, and checking the consistency and real-time processing. Now, the second part of this tutorial mentions that we wish to be able to change the parameterization of GNU Radio from external piece of software. So let us quickly introduce two concepts from computer science, the threads and the server client model. A thread is a piece of software that will be executed in parallel to the main software, sharing memory, as opposed to forks, which will create a new environment. The thread will share variables with its spawning software. So in this example, we have created a Python thread where we see here the definition of a thread, which might receive an argument, and the threading library from Python will allow you to create multiple threads and possibly provide different arguments to each one of these threads. So let us quickly see how threads work in Python. There is little point in watching us type the program, so let us look at how it looks like. So we created a variable that is shared by all the instances of a thread. So here we have 3 copies of the same piece of software that will be executed. This global variable will be accessed, and the classical issue with having a global variable shared by multiple threads that might handle this unique variable will be to the consistency, which is taken care of by mutex, by mutually exclusive access to this variable, and we will display the argument every second. So if we look at this example, we can execute the thread here, and we see that indeed all 3 threads are executed simultaneously. They will each have their unique ID, and they share this variable. We actually also see that the execution sequence might change over time. Here we have 1, 3, 2 that has been executed, while here it is 1, 2, 3. So now that we're familiar with the thread concept and the ability to run a second piece of software in parallel to the main scheduler function, let us see how we can communicate between the external software, the client, and the server. By definition, a server is the piece of software that expects a connection from the outside world, that is waiting for the connection. The client will be the one connecting and creating the link. So the various client-server models are either connected or streaming the datagram. So if we look at the socket man page, we have here the definition of the various IP communications. So we see here that we can have either a stream that is a reliable two-way connection, which is the TCP communication model, and we have the datagram, which is the UDP model, as was just seen with publish subscribe, where data are just thrown on the network, and if no one collects this data, then they are just lost. So in this example, although the data streamed from GNU Radio Companion would be just collected by Octave sometimes when bursts of data would need to be processed, in the case of commands, we want to make sure that each and every command is properly transferred from the client to the server. So in this case, we will create a TCP server. All these concepts are well described in Stephen's TCP IP Illustrated. So what does this TCP server look like? If we have a quick look at the piece of software, we need to import the socket capability of Python. We create a socket which is a stream, so a TCP server, to make sure that each and every command is indeed transferred, as opposed to the previous case where we could waste some of the data streamed from GNU Radio Companion to the external piece of software. Here we want to make sure that each and every command is transferred from the client to the server. Having done this, we create the socket on a given port here on the local host, and once a client has connected, we accept the connection, we get each command from the client to the server, and we act accordingly, possibly quitting once the queue for quit command has been received. So we can execute this using Python 3 interpreter, and when the server is connected, we can launch a client, and connect to the local host on port 4242 to send command. And of course, Q is the function for leaving, or we can send over command that will be processed until we reach Q. So we see here why we had an infinite loop. In this example, where infinite loop allows us to launch a new server whenever the client has quit the connection. So this will allow us to have multiple instances of sending various commands to the GNU Radio companion from a client. So here is an example of how we can put together all this information, and let's try to run this example together, where we wish to have a thread executed in GNU Radio companion that will change parameters of this flowchart. So let's create a new empty flowchart where we consider a signal source, and this signal source will have a frequency defined by a variable f, and this variable f will be tunable from an external piece of software. So let's make this variable f define the frequency of a source, which is throttled again, and will be displayed on as is on a spectrum analyzer, so the frequency sink. So how can we make this flowchart interact with the external board? So let's make this a demo, and we save this in a directory for modification. So if we just run this, of course, we just get the spectrum output, very little interest. So how can we make this interact now? So first of all, we wish to create this external thread that will interact. So to create a piece of software, we need this Python snippet, and this Python snippet will allow us to include some sort of Python commands, either after initialization, after starting, or after stopping. So let's just try a very basic example where we print a message when executing this Python snippet. And if we have a look at the console output when running this, indeed we see now that we have this hello message, meaning that this piece of software has been executed. So rather than just displaying a message, we might want this snippet to actually launch a thread. So this thread will be implemented in an external piece of software, which is a Python script. So we search for the Python module, and the Python module will be called EPY module 0 here. This is a name that is given by GNU Radio Companion. And we will create the thread function by creating, for example, this name. And this thread function here might, for example, just display a message at the moment, which is just something that mentioned that this is a thread that is being launched. Now, once we've got our thread function, we need to call it, and to call the thread function, we need to import the threading capability of Python, and to launch. So we threading.thread launch, and we mentioned that the target is this module that we just created, so the EPY module 0, and we call the main thread function that we just created, and this has to be started. So this is the demonstration of how we launch this external thread. So here we see that we indeed have hello thread, so meaning that the thread has been launched and GNU Radio Companion is executing. So now we have indeed this capability of creating an external piece of software and running, for example, a server in this external piece of software. So let's demonstrate that indeed the thread is running. So if, for example, we wish to have some timing capability, we can import the time function, and we can try to run this infinite loop where we increment a variable which has been created just above here, and we display the value of this variable to demonstrate how the thread is running. So here we print n, and remember to introduce some sort of latency to make sure that you don't overflow the capability of GNU Radio Companion. So we have a delay of 1 second between two increments and display. And so if we run this script, we indeed see that once every second the counter is incremented and displays its value. Now, at the moment, we have an external thread that is launched, that is executing every second. But if we try to stop the script, the thread keeps on running on the background. So this means that we now need a way of killing this thread. And as it is now, the only way is to actually identify the executing task and to kill the thread over here. So now we need to find a way of telling the thread to die when GNU Radio Companion is stopping. So we need to pass arguments to the thread. How do we do this? We create an argument to this function here that will be, for example, a variable that says we need to stop. And we test if this variable has become equals to 1, then we break the infinite loop. So this will be our solution for stopping the thread when a command is sent from the main program to the executing thread. Now we need to find how to provide this function to stop. And this variable will be passed as an argument over here. So this time we have an argument that is provided after launching. So we add that the arguments is equal to this stop variable that we wish to create, which is of course created here as we should not stop at the moment. So we create this as being equal to 0. Now we wish to set the variable when we quit. So we create a new snippet, and this time the Python snippet will execute when we stop. So this is after stopping, and we will say that the stop variable is set to 1. If we just do this, first of all, when we generate the script, we will see that the script that has been just generated indeed includes our function. However, the snippet that is executed after the initialization and when the program stops are actually two different functions. These two functions are over here, and we will create two local variables which are gmfstop and gmfstart here and stop over here. So if we wish to have these variables being shared, we will declare them as a global variable so that they know that the two functions will run the same quantity. And we need to continuously monitor the status of this variable so that we will create this variable here as a lambda function. So this lambda function will be the current value of this variable, and we will continuously update the value of this variable, so that this time over here this variable is no longer has to be evaluated, and here we create the evaluation function. So thanks to this capability, now we have this global variable that says we wish to stop. This variable will be updated continuously and actually we need to have a list here of arguments, and the Python snippet will change the value of the variable so that the thread stops when we quit the GNU Radio execute. So this time, if we execute this, we indeed see that the thread starts, it is counting, and when we stop, it actually stops the execution. Actually, we can check that it is stopping by displaying here a message stopping thread, and this way we make sure that the thread is stopped when we quit GNU Radio Companion. So here we have the thread that is starting, counting every second, and finally when we stop, we indeed see that the thread is stopping. So finally, now we wish to have this thread tuning the parameters of GNU Radio Companion. So we have this variable f that we created, and what we've seen earlier is that this f function would create this setter and getter, so this set function and get function, which would indeed change the frequency of the source block. So what we need is to change. So we see here that we have this f function here, and we have set f, the consequence of changing f. So here we can say that whenever we increment the value, well, we can say that, for example, the block dot f is equal, let's say, 1,000 times n, and we can run the set function of this quantity here. Now, what we need is to be able to pass the implementation of the set f. So we will provide a new argument here, and this new argument that we provide to the thread will be the self function of here in the Python snippet launch. We will provide the self of the coding program, so that the functions, the callback functions of the original launching program will be accessible to the thread. So here, self will refer when we create the executable here. We have indeed the creation of the thread, which provides self, and self will refer here to these callback functions that we have here, setf and getf, and the f variable here will be the same as the argument that we provide. So by executing this example, we see that indeed every second the frequency of the calling function is changing according to the execution of a thread, and if we stop the execution, the thread is stopping. Whenever we launch again, we see that indeed the frequency is being set by the external piece of software. So to summarize everything that we've done here, we have the external piece of software that is created as the Python module here, which we created by providing the stopping capability of this external thread and providing the pointer to the local functions of the launching program. We've been able to change the value of a variable of the calling function as well as the value of the blocks, and we stopped the thread. This piece of software is executed upon initialization, where we execute the snippet after initialization with various messages, and this global variable that will also be used for stopping the execution of a thread. And in conclusion, we have expected result of an interaction between an external Python software and the GNU Radio Companion flowchart. So now that we've demonstrated threading capability, all we need to do is to add in the thread the server, which we will do quickly and not record. No point in watching us type some software. So we've taken the exact piece of software, but this time we replaced the counter running with a timer and a sleep function with the socket. So this time we open the socket, we connect to the socket on the port 4242, and we listen for a connection. Whenever we get a client connecting, we receive, as we've seen earlier, and in addition to the quit function, this time we will get the frequency increment command. We will increment this time the variable, not as was done earlier under a time consideration, but when the command is received, we change the frequency and we set the frequency. So if we now execute this flow graph, we see that the thread has started, and we can run a client which connects to the local host 127.0.0.1 on port 4242. We see that we are connected, and whenever we increment the frequency, we see that this external software will connect and change the parameters. When we quit, we have disconnected from the server, and if we stop, since the thread has stopped handling the connection from the client, the flowchart will stop. So this demonstrates that we can have this external software. In this case, it was a telnet client, interact with GNU Radio Companion and change the parameters of, in this case, the source. So this wraps it all up. We see that by combining Python module and Python snippet, we can launch some function. In this example, a thread. This thread has received the self argument so that we could tune the launching function variable and callback functions. And by running the telnet client, we could interact with the parameters of the frequency source. And we've seen, on the other hand, that ZeroMQ allows us to stream the data to an external software, in our case Octave, and to process the data. So to conclude this presentation, what was the practical use that prompted this whole investigation? We wanted to assemble this radar system using software-defined radio. In this example, we had a synthetic aperture radar. In this case, this antenna is a reception antenna. The emitting antenna is static over here. And the source is either a frequency step continuous wave, in which we tune, as was done right now, the source frequency, or it can be a noise source. In this example, Wi-Fi is quite close to noise. So here we have a Wi-Fi dongle which continuously streams data because this noise needs to be collected on a reference channel. We see here that this noise source feeds one channel of a B210 dual channel receiver. The second receiver is connected to the antenna, and cross-correlating the reference measurement with the received measurement allows us to measure the range to target. Now, initially, as we were doing this measurement, we got several echoes with the antenna located at a given location, and we wanted to know the azimuth from which these echoes were coming to check whether echoes were coming from these cars parked over here, from the roof of these parking lots, or from the house on the opposite side. And to get azimuth, we needed to move the antenna. Moving the antenna meant attaching it to a rail, and this rail is motorized. This motor is driven by a microcontroller sending commands. Indeed, the scheduler of Linux would not allow us to precisely move this stepper motor because the time interval between clocks is not deterministic. So in this case, we have a dedicated microcontroller generating the clock signals to move this stepper motor, and the stepper motor control is driven by this external piece of software which collects data from the antenna, cross-correlates the reference and the measurement, and once processing is completed, will start moving the motor. Now, the motor takes a few seconds to move the antenna from one location to the other, so that the data do not need to be streamed continuously as the antenna is moving and the measurement is not stationary, and only when the motor has completed its task will a new data set be collected. In this example, the motor is controlled by the UART, the serial port of a microcontroller, using the instrument package of GNU Octave. So to conclude this demonstration, here is an example of a synthetic aperture radar image of targets. And interestingly enough, what we see is that the strongest targets are actually generated over here by the house on the opposite side of my apartment. And here actually the strongest targets are due to these roofs. If you can look closely, these various parking boxes have some roof with some metallic coating to make it watertight, and these are at right angles, and these will act as corner reflectors. So quite surprisingly, the strongest reflections are not these cars parked on the left side of this image, but it's actually the corner reflector-like shapes of these right angle interfaces between the roofs of these parking boxes. So here is this synthetic aperture radar image that was collected by illuminating using a Wi-Fi covered emitter, just streaming random data to illuminate the scenes. So we've demonstrated how to make interaction between GNU Radio and the flowchart generated by GNU Radio Companion with external tools, feeding these external tools with bursts of data, whereas the data stream from GNU Radio are contiguous, which is needed, for example, when phase alignment has been calibrated. See, for example, the presentation by Clément Campo and others about phase alignment on the X310. And this framework, although they've been demonstrated in this tutorial on a single same computer, this is best achieved for making embedded hardware communicate, for example, with a host PC. In our case, the radar streams were collected using a Raspberry Pi and the USB 3 interface of a Raspberry Pi 4 with the laptop connected to the Raspberry Pi for an Ethernet link. So see the tutorial by Gwenaël about running GNU Radio on embedded hardware and the Raspberry Pi. We believe that this strategy is a fruitful alternative to creating custom out-of-tree blocks rather than having to comply with the framework of GNU Radio and the work block running continuously. This will allow us to implement in external languages, in this example Octave, but might also have been Python, some processing tools. Finally, this conversion of continuous streams to burst processing might have also been handled using the tag capability of GNU Radio, as is often done in a digital communication context, and this will be addressed in the tutorial by Thomas Lavarenne and Cyril Morin about using tags in GNU Radio. And with this conclusion, I thank you for your attention.
The goal of this tutorial is to present the use of GNU Radio on embedded hardware with an operating system built by Buildroot. This tutorial is split into three steps. First one is a presentation of Buildroot and a comparison with some distribution like Debian or Ubuntu. After that, we will download a Buildroot source and to configure and build this. And finally, we create two Flowgraphs. The first one is executed on a target board and contain a signal source and the ZeroMQ publisher. The second is on the PC side with ZeroMQ subscriber and a plot to display the signal received from the target. So, what is Buildroot? Buildroot is a build system. This type of tool is used to build a full operating system. This means, and the first task is to have access to a compiler. Usually, when the host computer is based on an Intel processor and the target has a different architecture, it's a cross compiler. This tool is dedicated to be executed on a host computer, but to produce binaries targeted for the embedded platform or in different architecture, ARM, PowerPC, RISC-V, etc. The second task is to build a bootloader. Bootloader is quite equivalent to a BIOS, and the kernel to deal with hardware access. The next task is to populate the root file system with libraries and applications selected by the user. And at the end of the build, it produces a disk image. This file is used to write SD card or SPI flash or an eMMC or a drive, of course. The interest of this approach is to have small disk space and small build time. Small disk space in host because only the selected tools and library are built, not everything. And by selecting some option or sub-option, it's possible to reduce or to really target a specific application and small build time for the same aspect. In a specific case of Buildroot, resulting image disk is a firmware. This means it's not possible to modify or to update, install, uninstall application or library in live. If something must be modified, you need to go back to Buildroot to update the configuration, to build again, and to flash again. But why using Buildroot? It's true. Modern distribution like Debian or Ubuntu may be used with for different architecture, Intel architecture or ARM, PowerPC or RISC-V. The good aspect of binary distribution is the easy to use. You select, you install an application, everything, all required dependencies are automatically installed by the package manager. And it's fast because everything is already built. You fetch binaries and you don't lose time with a build, with configuration of each libraries or application. But it's not targeted for a specific CPU or specific version of an architecture. No, it's targeted on global processor. For example, all ARM or all PowerPC or all RIS file. So it's not possible to take advantage of a specific instruction for the latest generation of Intel processor, for example. The second drawback with this approach, the maintainer decide which options are set or unset, and consequently, if the maintainer decide to enable everything, the final binaries is high, and this increases the storage space. At the opposite, Buildroot and the firmware produced by Buildroot is tailored for the specific architecture. It's not generic ARM, but it's specifically for a version of ARM, for example, Cortex A9, and consequently, every instruction are available. The second aspect, it's tailored for an application of a goal. You need an embedded board for a specific task. You select every package required, not rest, and you have something really optimized for this task. But since every package must be built, it takes time, big time compared to a binary distribution, and it's not possible to update in live your system. You need to rebuild after having modified, updated your configuration. But to compare a bit this two approach, Buildroot with GNU Radio may be used with a Pluto SDR and fit the SPI flash. It's small, but this space is enough to support Buildroot GNU Radio Python. Volk with Raspbian can't be used, optimized, and floating point unit available on processor, on ARM processor, on Broadcom processor, because this distribution may be used for Raspberry Pi 1, 2, 3, 4, and consequently is 52 bits. Neuron may be used with Buildroot with a better performance, around 6 times better than a generic implementation. Okay, we have seen basic, so we more closely to Buildroot structure. The tree or the directory of Buildroot look like this. There are more directories than that, but it's most important directories. The first one, configs, contain the bare minimal configuration. Each configuration address one board. There is a configuration for the Raspberry Pi 1, Pi 2, 3, 4, BeagleBone, BeagleBone Black, Beagle 5, etc. By bare minimal, I mean it's the strict required set of application and information to be able to build a system and to have a bootable image. The model of the CPU is provided, the version of the bootloader, the version of the kernel, but there is really no application. There is no SSH server, nor client, etc. The second important directory is package. Package contain a big 2,000 subdirectories. Each of them contain recipes to build an application of library. Provide the relationship between an application or library and other application or other package, to be short. where to download, how to configure, how to patch, and how to build the corresponding package. The last one is the output. Output is working directory, the Buildroot working directory with some important subdirectories. The first one is the host. It contains all tools able to be used by the host computer to do something with target. It contains the cross compiler. It contains, for example, if QEMU, an emulator is set, it contains QEMU, etc. Every tool used by the host computer. Build directory is the location or where all packages are extracted, built, configured, built, and not the last. The target directory contains it's the image of the future image disk. This is here. All packages are installed after the build step. And finally, the output image is the final image location. In this directory are installed the bootloader binary, the kernel binary, and the root file system partition, and finally the image where everything is provided to flash an SD card. The official Buildroot provide plenty of config, plenty of package, but it's possible to extend. The bar minimal configuration are sometimes boring because you need to configure each time you start with a new Buildroot which package you want. It's possible to create a custom dev config, but it's not a good idea to copy this each time in the Buildroot directory. Better approach is to use a BR2 external. This is maybe seen as a lawyer to extend Buildroot by configuration, by new package. There is two examples. The first one, Pluto SDR, is focused on Pluto SDR and provide every tool needed to use this. Is same approach. It's the same target ID to the official analog devices repository, but in more easy to maintain. The second one, OSKIMP BR2 external, is a most generic external with Raspberry Pi 3 and 4 configuration with GNU Radio already set, and some new package like GNSS SDR. One important thing to finish with the aspect of Buildroot is first I've talked about the relationship. There is two types of dependencies between packages. The first is the select. It's most easy to understand because a package, for example, some module of GNU Radio depends of the FFTW library. This library has no many dependencies or many limitations. For example, not compatible with some compiler or something like this. So some package GNU Radio modules may use select to automatically set this library without any manual intervention. At the opposite, there is depend on. The user has to manually enable dependency. It's, for example, again with GNU Radio, Python 3 needs to be, or Python needs to be explicitly enabled by the user. Because first, it's possible to use Python 2 or Python 3, so it's not possible for Buildroot to decide which version to use. And Python has many dependencies, many limitations, etc. And consequently, it's to the user to select everything to fit, to match dependencies, to be able to use this interpreter. The second issue, maybe, with dependent is if all depend on for a package are not satisfied, the package is not shown. So it's difficult to see if the package is possibly usable or just absent to Buildroot. The second important thing is the pitfall. The first one is a classic pitfall with the modification, the update of the option for a package. If the package has already been built, if you select enable some sub option, and you just use make or rebuild the image, the package will not be updated, rebuilt, reconfigured, and rebuilt. You need to explicitly use the reconfigure and make. The second thing is the toolchain modification. In all cases, it's required to use make clean to suppress everything and to do make again. A toolchain modification is, for example, when you change the C library or you enable the C++ compiler or something like this. Last one is when you select a package with select for another for a dependency. It's required, it's better to check if this package is if this a sub option of a package or a new package, because it's a sub option is the same problem as second point. An important thing to flash your SD card. The most common command is dd with a source, usually the SD card.img provided by Buildroot, and destination. The destination is usually a SD card, but it's really important to double check if the /dev/something point of your SD card of your hard drive. This command will bit-to-bit overwrite the mass storage, and consequently it's not possible or really difficult to recover data lost, or simply the partition. Okay, we have seen basic of Buildroot. Now we will see modification needed on Buildroot to have access to GNU Radio. First thing is about the toolchain. By default, Buildroot provides the uclipse, a C library, light C library, with some lack of support of not fully supported specification. Consequently, it's required to change this option to use the glibc, a more complete version. Usually, this is the version used by all distribution. Since GNU Radio is written in C++, the C++ compiler needs to be set. Last thing is when to move file through the host computer and your target. One way is to use a SSH connection with a SSH server, SSH client, and SCP. So we need to set drop bear, lightweight version of SSH client server, and to be able to use SSH, the user by default root must have a password not provided by default. So it's important in the system configuration to provide a root password, for example, root. Last thing, again, with the idea of depend on, Python 3 must be set to have access to Python support. And finally, MISC cancellationus need to, in MISC, you need to set GNU Radio, block support, Python, analog, and ZeroMQ to have access to all required blocks for this demonstration. And finally, devconfig provide a really small size partition, and it's not enough to with Python 3 and GNU Radio, so it's mandatory to increase the size for something with better to fit requirement. After the theory, now it's time to do a bit of practice by playing with Buildroot. But first of all, we need to download an archive of Buildroot to the website buildroot.org. This provides some interesting things like documentation, but now it's download. We use the latest stable release. The file is quite small, and now we have this one somewhere. To extract, we need to use tar-xvf, extract verbose, the file name, and to move to the directory by using cd buildroot. The content of the directory look like quite the scheme presented earlier, and now you need to apply the default configuration. There is around 260 different dev config to allow for everyone to do some tests without real hardware. We use make. All commands start by make with Buildroot, and we use QEMU, an emulator for ARM processor. This devconfig provide set QEMU, so there is no need to install this package by using the package manager of your distribution. So just doing this. Now the full configuration is applied. It's time to open the config panel by using make menu config. Enter. So it's curse interface. So to move between menu or option, you can use up and down key, page up, page down, or simply using key or the letter in blue in the menu. For example, first and to move in subdirectory, you point the subdirectory and you use enter. Here we need to switch the C library by using glibc. Again, we need the C++ compiler. To move to up in upper directory, first we need to use tab to switch to option at the bottom of the screen by using tab. This allows to move, to exit, and using enter. Second, system configuration, to configure the root password. Again, enter to select, for example, root. OK, enter. Again, exit. Now we need to select all required package in target package. One useful command to move quickly to a specific package is to use slash to have a search menu. And for example, for drop bear, use search this. There is potentially many options. Here it's the first, and near all options there is a number. Just choose corresponding number to go directly to this option. Here it's okay for that. Now we need to enable a Python free interpreter. It's located in the interpreter subdirectory. Again, enter, move to Python, select by using space bar, and up to the upper level. An interesting thing again with GNU Radio, specifically for Python, for example, is information explained earlier with dependent and select. Select, so everything is automatically will be set if this option is set, and it depends on this one. So this it's a logical or and etc. And for example, here we need to have the higher level package GNU Radio set to be able to have this option displayed. Here in MISC, GNU Radio, there is no other option displayed. If we enable this, we have everything. So you need blocks, you need Python to execute scripts, ZeroMQ to transmit a stream, and analog. Here it's an example of select. Analog use FFT and filter. So these two options are set, and the dash explain it's not possible to disable these options. So exit, exit, exit. We are upper level. So the configuration panel asks you to save or not your modification. Yes, of course. It's possible. When you are happy with your configuration and you want to save this to reuse more than one time, it's possible to use make again, save, def config. This will overwrite the default def config used. This takes a bit of time. If you read QEMU arch def config, and you see GNU Radio is set. Drop bear true. The root password is set. So this the def config has been updated with your specific needs. So now it's time just to type make to build everything, cross-compiler, file system, etc. And finally, to have access to binaries, file, ready to be used with, so to flash on a card or to use with the QEMU. So now make. Okay. It's time for a coffee time because this take a bit of time because everything needs to be fetched, to be extracted, compiled, etc. So it's some common use. So you need to download this. You need to extract using tar, to apply a bar minimal configuration by using defconfig bar minimal or your custom configuration, to select package by using make menu config to have access to the configuration panel. The build is done by make, and if you have a real target board, it's possible to flash an SD card by using sudo to have super user write dd. If is the source, here it's SD card.emg, and destination by using off /dev/ something. Take care to the destination. Again, it's if you use the wrong SD something, it's possible to lost content of a hard drive. There is some tips. First is for this time we have just to use one Buildroot, so it's okay. It's the first time, so all files must be downloaded. But it's useful if you have more than one Buildroot and to gain a bit of time by not downloaded again the archive, to use br2 dld to specify a path somewhere where everything will be downloaded instead of in the dld in the Buildroot directory. It's a good option. The second thing is to use br2 cch in menu config. This allows to reuse some already built part of file. The C file is compiled in an object file, and the cch allows to store some parts of this process and reuse this to gain a bit of time again. To avoid to lose too many time, if you want to start quickly, it's possible to download all file required for the next step in at this address. After a delay, depending on your host computer CPU and your internet connection, the Buildroot task is done, and now you have this message, and everything is okay. Before starting the new system through emulator, we will see a bit to the output directory filled by Buildroot. So we have build, host, image, target. Staging is a specific directory with libraries targeted for the embedded system. First, we have the host with all tools for your CPU, for your PC, to deal with the system, to build something with cross compiler, C++, C compiler, etc. You have some, for example, automake, everything required, and you have an emulator dedicated for ARM processor. Second directory is a build directory with everything built by Buildroot. So everything with the host is for the host, of course. You have FFTW required by GNU Radio, some C library, GNU Radio, etc. Everything selected using the menu config. Target is the future root file system. And finally, image, where are stored all binaries for your target, with the kernel image, the root file system partition, it's just a link, and a script with basic functionality to boot the new system, with the emulator and some information, but it's not enough to be able to use our system and to use ZeroMQ subscriber and publisher. So again, binaries. This one is a complete line required to use the emulator or system for the specific goal. We have the emulators in just earlier, the machine type, the target CPU. We don't want to have a graphic interface, just one CPU, the path to the kernel image, command line to say where the root file system and which console, which terminal to use. But the most important thing, the rest is less important. Most important thing is the internet connection is used by user mode. This is the name of the interface, and since this emulator in this mode acts as a proxy between the host and the guest, we need to forward all ports required for this demonstration. The first one, this is the guest port, it's the host port. Maybe different or the same. For this, the 22 port is the SSH connection. But since it's possible to have an SSH server running on the host computer to avoid some conflict, we map this guest port to another port with an number to allow user to create this one. The second port is a port used by ZeroMQ. It's not required to have exactly this one, but we have selected this, and we forward the guest port to the host port with the same value. So now, if we use this and start this in a terminal or new system, boot, we see a DHCP client working with a proxy and the interface provided by the emulator. The SSH connection are started, so we need to use as login root, password root, or something I've used for in a menu config, and we have a prompt with nothing. But if we see this one is the architecture, so it's match. This one is show. It's a Buildroot built this day and for ARM64 processor. So this prove we use the correct system. To use the ZeroMQ for the publisher in a target side, we need to use the public address of the interface. To know this one, we use the ifconfig command to show the local interface, not shown at the outer the system, and the public interface and the public address. This one must be used when in a Flowgraph in a GNU Radio. Now it's time to start with the GNU Radio Flowgraph. The GNU Radio demo will show this. Two Flowgraph, first one on your target side with a signal source to have a fake acquisition device, but instead of processing the data stream in the board, everything will send through ZeroMQ to your CPU or your host CPU, to just in this case using a Qt sync to display the signal source. For both Flowgraph, GNU Radio will be used. The first Flowgraph will be exported in the Python file, and this file sent to your target to be executed using the command line interface. The second one may be executed using the command line on your computer or by executing through GNU Radio Companion. So first, we need to start GNU Radio Companion, of course. First, for the target Flowgraph option ID, we need a valid ID to comply. The generate option by default is configured to use a Qt GUI. So our board or emulator on Buildroot has no support for this one in this current configuration. So we need no GUI to just have a command line interface. It's all for options. We need a signal source. For this specific demonstration, we left unchanged. We don't have hardware to have a real sample rate, so we need to use a throttle, and we need a ZeroMQ publisher sync to send stream to the computer. This block must be configured by using again the public address of the board using TCP address port. This one used in the emulator configuration. And it's all. Save this Flowgraph, and we generate the corresponding Python file. This file may be sent to the board using SCP, secure copy, using network. Since it's not, we use a custom port instead of the official 22, we need to use the dash IP to provide the address, login arrobas, and it's a bit hard, but we need to provide the local address because QEMU act as a proxy. And finally, the directory where to store this file, for example, /tmp. Sorry, most important, the Python script, and it's failed. It's not an error. It's just to explain. If you have already used your Buildroot or something in localhost with this IP, the key generated by the SSH server at the first boot is stored in a specific file. But if you build again your file, you lost this key, and SSH server will automatically generate a new one. And there is a mismatch between the stored previous key and the new key, and it's maybe a man-in-the-middle attack, or maybe just the key has changed. So SSH is friendly and provide the command to suppress previous key. It just requires to execute this command and to try again. This host is no more known, so we need to accept the new key, and you provide password. If go back to the target, cd/tmp, and the script is now available on your target. So now, second Flowgraph for your computer, PC demo, for example. This time we need to use a Qt sync, yes. So we left generate option with the default value. This time we use subscriber source, and again TCP, but as for SSH we use the local address, and again support. No hardware, throttle, and Qt sync. save, of course. This time it's possible to use directly this new one. Not required. It's okay, nothing. We see nothing because the script is not ready. We launch by using /script name. And after a bit of time, because it's the first time GNU Radio is used, some file, and we see the signal and the frequency match the 1 kHz frequency configured here. So this proves we are able to use GNU Radio using a target on embedded board or an emulator to test or to demonstrate some concept without having access to the hardware. So now we have seen how to use GNU Radio with basic demonstration, but this use quite nothing in the functionalities and capabilities of the CPU, and finally modern board have plenty of resources, multi-core, Raspberry Pi has 4 core up to 1.5 gigahertz. Another one, the Rock Pro, has 5 cores at up to 1.8 gigahertz. Large RAM capacity. It's usual to see board with 2, 3, 4 gigabytes of RAM. Large storage, eMMC or SD card has plenty of resources. It's possible to connect display, etc. So this using this type of board to just resave and transmit, it's useless, and it's possible to add more processing and to have maybe the embedded board as a standalone device with a pre-processing or full processing, and for example with a cute plot to display a result. There is some small examples. The first one is Pluto S0 as a FM receiver with audio out with a modified bit stream to have a sound card, to integrate a sound card in the FPGA. So this board, in this configuration, the Pluto S0 receive FM modulation, do everything, and finally provide this to an ALSA audio sync, without having the need to use an host computer. The host computer finally is only required to start the application and to configure the center frequency, and it's all. The demonstration is explained in the OSKIM digital repository in subdirectory tutorial Pluto S0, etc. And the corresponding BR2 external is available in again in the GitHub OSKIMP. And another example is Raspberry Pi with big of resources with an OSRP B210 connected on with USB 3 interface and GNSS SDR, the package, the application directly used on this board. This allows to have a standalone GNSS receiver. The GNSS SDR is not officially in a Buildroot. There is some prerequisite to fix before contribute this package. So currently it's available again in OSKIMP underscore BR2 underscore external, and more precisely in the package as GNSS SDR. So now to have a second funny demonstration, we start directly. If you have a real board, it's possible to directly update your configuration. For QEMU, the first demonstration use as a virt machine, and without a device tree. The device tree is a description of the hardware. It provides the CPU type, the peripheral available or not, controller and peripheral. So it describes really the configuration of the board instead of a big file. It's a current, modern, and stable way to have this description. So for QEMU, it's required to move to another dev config. So it's required to rebuild everything. It's not required for this tutorial because binaries are provided to do the task, and the Buildroot configuration must be updated to with configuration previously applied in the first demonstration. But it's required to add the Qt5 because due to the complexity of this package, it's not possible to use only a select. So it's required to manually set this. Qt5 has no default font. So, for example, liberation font must be set to have legend and every text on a Qt plot. And finally, it's required to enable the Qt GUI support in the GNU Radio. It's time to play again with Buildroot and with make menu config. Everything must be done in target package menu and font submenu to enable liberation font. Next, graphic libraries and application to enable Qt. And finally, MISC to enable Qt GUI. Just a parenthesis, I've not mentioned this earlier, but it's possible to use Osmo SDR, to use DVB-T key, and it's possible to enable UHD, to have access to USRP device. Since UHD, the library is has no complex dependencies, it's possible to use directly a select and to use this instead of having to enable the library before having access to this option. It's all. For configuration, it's all. Again, as mentioned earlier, GNU Radio configuration has been updated, so it's required to use reconfigure to explicitly force Buildroot to apply all steps to this package, and finally make to build and to generate a new image. So now the QEMU command, some modification must be done in the command line because the VExpress board is based on 32 bits instead of 64. So we need to use system QEMU ARM. The virtual machine VIRT for this option is replaced by this one. To demonstrate, we use 2 core by using SMP, small RAM. This time we have a device tree, so we provide this file using this option. The root file system point to a real or emulated device instead of a virtual one. Since we want to use the display, we suppress the no graphic option, and we append with the serial with the STDIO to have the prompt in the terminal, and we enable the VGA by using STD. This time we need to use the package manager because the Buildroot version seems not to have a display support. And an important thing when we use Qt, there is many driver, many options to use frame buffer, OpenGL, etc. So we need to provide by a shell variable which driver to use by using this command. So now I don't need, I've already built this. So we use this one to boot the new system. We have a new window with the display equivalent to a screen connected to the board. The number of tux is equal to the number of core in the for the specific board. So since SMP is equal to 2, we have 2 tux. Now a bit of GNU Radio Companion with a new project. For example, Qt demo. This time we have Qt on the board, on the emulator, so this option is left unchanged. We need to have a signal source again. Theoretically, it's possible to connect a USB key to the host computer and have access to the QEMU, but sometimes it's not really stable. Again, throttle. It's finally the same as the previous Flowgraph with a signal source instead of ZeroMQ, and finally a Qt sync. It's okay. Again, we need the Python script. And again, we need to use SCP. In my case, the board has already booted, so I don't need to drop the key. We have first this one not required. Bit of cleanup, a big file, root and root again. We need to use this one for Qt to move to TMP where there is a Qt demo. And to start this one by using this one. And after a bit of delay, the Qt sync must be displayed on the virtual screen, virtual display of QEMU. So now we have exactly the same display as previously with the ZeroMQ connection, with the time sync, the frequency sync with again a 1 kHz center frequency. So first we are able to use GNU Radio and we are able to use an interface. just a small conclusion about this tutorial. GNU Radio is available in Buildroot build tools. It works on real embedded device or emulated, supporting ARM processor, RISC-V, PowerPC, MIPS, etc., or Intel architecture. Signal source and file source are not only solution. It's possible to use a UHD or Osmo SDR. And if you have this, Xterix device is available, not officially, but OSCIM Bear 2 external repository. And great thing with Buildroot is GNU Radio and everything is optimized for the targeted CPU instead of a generic CPU. Thanks.
Welcome to this tutorial on the management of tags in GNU Radio. I'm Cyril Morin and I will be joined by Thomas Lavarenne in the second half of this presentation. This tutorial contains several exercises and for each of them you will be able to work on them for 5 to 10 minutes. A correction file will be available about the halfway point. Let's get started. We will start this presentation by explaining what are tags and how they fit inside the data streaming process of the GNU Radio Flowgraph. And then we will put it into practice. We will begin that by creating a small flow graph to generate tags using standard library blocks. And then we will use this flow graph to create Python blocks that can first detect the tags and then use their different properties, such as offset and value. And finally, we will put all of this into practice using a more concrete example of the ADSB protocol. Okay, so let's begin by understanding what tags are. To do that, let's take a look at this animation. Here we have a very small flow graph, classical flow graph, with just a signal source, something that squares it, and a plot, a time sink. So we generate a sinusoid, and then we square it. That's a simple processing that we could have in GNU Radio. So if we now zoom inside the first buffer in this chain between the first two blocks, we can see that when the graph execution is started, we have chunks of samples, blocks of samples that are output by the source block. And each of these samples has a number, the offset. As you can see here, all of them are numbered. This number is absolute. It begins at the start of the execution and never stops increasing. And the receiving block also works on chunks of these samples. So these are the basic working of the work functions of the blocks inside of GNU Radio. The number scheme that we just talked about, the offsets, is independent from one buffer on one block to the next. And it depends on the rate at which the samples are generated. So now let's add tags to this stream. The tags are a way to add metadata to specific samples within a stream. And most blocks are able to propagate the tags they don't use to their output. If we zoom in again inside of the first buffer, we can see that the tags move in parallel to the main stream. They actually are just a data structure with 4 fields, beginning with the offset, which defines which sample the tag is linked to. And then we have the name and the value, which are user defined. The name is also called the key, and it can be also used to filter the type of tag we want to listen to. And the value is, well, whatever we want to put inside. And finally, we have a source field that identified the block that first created the tag. And by default, most blocks propagate tags by copying the content of the input tag into their output and just adapt the offset to the new buffer at the output. But the task of computing the correct offset to copy the tag may be quite complex, depending if the rates of input and output is variable and maybe if there is multiple output and outputs to the block. So some blocks don't do it properly, or some don't at all. Now that we've seen what tags are in theory, let's get practical. We are going to switch to GNU Radio, and I'm going to start with a flow graph that's available on the tutorial page on the website. So we have, as a starting point, a very basic flow graph. We have just a signal source that outputs a cosine wave that goes into a throttle, and we can plot it with a time sink. And if we run it, we can see that we have just a simple sinusoid. Now what we want to do with this is to add tags to this stream. The first way to do it would be to add a block called stream to tagged stream. We can find in the stream tag tools section. If we open this block, and first of all, let's start with using it with floats, we can see that we can input it a tag key or tag name and packet length. If we say 100 in there, for example, and if we plug it inside of the Flowgraph, and run it, we will be able to see what it creates. So if I stop this Flowgraph, we can see that now we have the exact same sinusoid signal, but we have on top of that, at regular intervals, so basically every 100 samples, we have one tag with the key on the name packet length and the value 100. We can also see with this that the Qt timesync is able to display the tag, which is quite useful for debugging. And so the thing is, this stream to tag stream does not allow us to choose what the value of the tag is. It's always fixed to be the packet length. So in our case, we will not use this block, but we will use the tag strobe block. Here we go. So if we open the properties of this block, and first convert it to use floats, we can see that this time we can choose at which frequency we want to put a new tag. So if we say I want a new tag every 100 samples, and we can choose explicitly the key and the value that we want for the tag. So in this case, as a basic example, we will just put tag and maybe value. The key is expected to always be a PMT that contains a string, and the value could be also a PMT that contains the string, so in this case the string value, but it could be also a PMT that contains a number or a dictionary, a list, or pretty much whatever we want. If we select that, we have now the tag strobe that has one output and a signal source. If we just look at what's going on at the output of the tag strobe, we can see that the block outputs just samples with zeros and at a regular interval the tag that we want. And now we want to be able to merge the two streams, so have the sinusoid of the signal source and the tags of the tag strobe. So to do that, we will use the block tag share. That's presented like this. And so it has two inputs and one output. If we select this, what this block does is that it will just copy the contents of the sample that goes into the input, and it will share the tags that are present inside of the share input into the output. And so if we plot this, if we use it like so, we can see that now we have our sinusoid and the tags. Now to get a bit more interactivity, we will add a way to select the frequency at which we have tags at runtime. And to do that, we will add a range, a Qt range, like so, that we will call, for example, tfrec. With somewhat sensible values. And we will set the tag strobe to use it in the num sample parameter. And so now when we run that, we get, just as before, the synoded and the tags, but we can change with the slider the space between the tags. While we are at it, let's showcase a feature of the Qt timesync that's related to the tag. We can add a trigger based on the tags. And when we do that, it asks us for the name of the tag or the key of the tag we want to select. So in this case, it's a tag. And so when we have that, we can see that we all the time have the first sample be a tag. And then we can change and really see the change of frequency. Okay, so now that we've seen how to add tags with basic library blocks, we will get to the next step, which is create custom blocks, in this case in Python, and use the API to manipulate blocks inside of them. And so what we will want to have is at the output, add a new block, in this case a Python block. We will work with embedded Python blocks, but we could also use AUT modules with Python or C++. It would work the same. And so we will add this new block in there. And for the next step, we will modify these Python blocks. This can be done simply by opening the parameters of the block and selecting open it into editor. Okay, and if we open it, we can see that we have a default block that does basically nothing. It just copies what it has at input and it puts it at the output and it multiplies it by the parameter. And so what we will need to do is modify it to use at input the type of samples we want to have. So in this case, floats. And we will maybe just remove the use of this parameter. Okay, when we save this, we can connect it and run it. As expected, we have exactly the same value for the original signal and the modified one. Okay, so now that we have the basic framework to play with blocks, let's get back to the slides. So the first thing we want to do to play with tags is to first of all detect that we have tags. So we have two ways to do that, or actually two functions. Both of them work similarly. They both allow to filter by tag name or the key, and they both output a list of tags that are seen. The difference between the two is that the getTagsInRange function operates with numbers of start and finish of range that are absolute, so the row offsets of the samples from the start of the execution of the flow graph. And the getTagsInWindow function uses numbers that corresponds to the beginning and the end of the samples available to the current forward function. So in most cases, the getTagsInWindow is a bit more practical to use because you don't really need to know where you are since the beginning of the execution of the flow graph. Okay, so now let's get to the first exercise. The first task will be to modify the embedded Python block we just had so it can mute and unmute. So either copy what's at the input or just put zeros in this place, and start and stop muting this if a tag is seen as input. Don't forget to import pmt at the beginning of the Python file, so we can use the pmt.intern to filter with the tag name. You now have 5 minutes to work on this, and at the halfway point I will make available the correction file on the website. Okay, so now if we open the correction file, so tags embedded part 1, that's available on the website, we get this. And we can see that the block mutes and unmutes. Sometimes we get zeros and sometimes we get the sinusoid. But it's not really related to the actual position of the tags. So the next step will be to make it so that the muting and the unmuting happens exactly on the positions of the tag. And to do that, we will remind you that the tags that we get in the list of tags output by the get tags in range or get tags in window functions, they all are objects in Python or C++ that have the 4 attributes of the key, the offset, the value, and the source. So we can use this offset, which is an integer, to find out the position of the related sample in the stream. So let's get to this. You now have 10 minutes to do this. And as before, at the halfway point, I will make available the part 2 correction on the website. Okay. And now if we open this part 2 correction from the website and run it, and maybe hide the original signal, we can see that now we have truly the mute and unmute functions that happens exactly on the positions of the tag. And if we change the frequency of the tags, we can see that it does match. The muting and unmuting process is still exactly on the tag positions. Okay. And now the third exercise will be to play with the values of the tag. And to do that, we'll just do a bit of setup inside of this. And we will make it so that the tag strobe has a value that is a number, first of all. So we can do this by putting as a value not pmt.intern that works on strings, but in this case pmt.toPmt that is able to operate on most Python types. And we just put maybe 10. If we run this, we can see that the value of the tags, maybe I'll stop it, is now 10 as we wanted. And to have it be a bit more dynamic, we will add a new range that will allow us to select the value of the tags at runtime. So if we add val, between maybe 1 and 100, that's fine. We can now use this new parameter in there. And when we run it, we have as a base the tags that have 50, so that's to be expected. And when we change the value of the tag changes with it. Okay, so now that we have a bit of setup done, the next task will be to have the block start muting when a tag is received and mute for as many samples are in the value of the tag. So for instance, if the tag says 50, mute for 50 samples after the reception of the tag. So now you have 10 minutes to do this, and as before, in the halfway point, you will have the part 3 file available on the website. So let's check that it works properly. If we open the tags embedded part 3 and that we run it, I will add a trigger to the tags so that we can see a bit better. Okay, so now that we always trigger on the position of the tag, we can see that if we increase, for example, the tag frequency, we have tags a bit less often. And if we zoom in and just plot the samples exactly, if we count them, we can see that we have truly 10 samples, which is the value of the tag. And if we change the tag length, we can see that the number of zeros changes with it. Okay, so now that we've seen how to read the two main fields, which are the offset and the value, I will leave the floor to Thomas, which will talk to you about how to write tags in custom blocks, as well as the operation of several other types of basic standard library blocks.
Okay, thanks to Cyril for this first part of the tutorial. I'm Thomas Lavarenne, and we will now take a concrete example in which the tags will be used to preprocess the ADSB frames. But first we will need to understand a little what is ADSB. So what is ADSB? ADSB, Automatic Dependent Surveillance Broadcast, is used in civil aviation to transmit parameters of the airplane to the ground stations or to the airplane. You can find everything on the mods.org website. Let's watch just a moment. Okay, click on read the 1090 MHz reader. Here you will find absolutely all the information about ADSB frames and how all the different parameters are implemented, if you ever want to decode them later. So just have a look to ADSB Basics. In ADSB Basics, we can find the frequency of 1090 MHz. We also find that the frame is 112 bits long, and we find that for civil aviation, the message starts with a downlink format with value 17. It corresponds to 10001 in binary. That's for the first 5 bits of the message. Okay, let's go back to the presentation. So, the important parameters are ADSB use amplitude modulation at 1090 MHz, and ADSB frame is 112 bits. It uses pulse position modulation, and bitrate is 1 megabit per second. Now, let's take a closer look at the start of the frame. The frame starts with a preamble of 8 microseconds. Then we have the downlink format, DF code, with value 17. We can see that logic 1 is transmitted by varying the amplitude from a high state to a low state in the middle of the duration of a bit, and vice versa for a 0. We can consider that it's a bit similar to the Manchester coding. But what interests us more precisely now is that by choosing the sampling frequency at 2 MHz, we can obtain a signal containing 2 samples per bit. Okay, now it's time to practice. You have a file, a GRC file, adsb.tuto.grc, which is already pre-completed. You can use the instructions below to observe the ADSB frames. You can open it with your GNU Radio. We will let you 3 minutes to observe and play with this file. Then we will look together what's going on more precisely. Okay, here we go again. Let's look together what's going on. Here we have the file source, the throttle, the complex to max squared that inputs the amplitude, the threshold that outputs only 0 or 1, and the time sink. If you run the flow graph, we see many signals. As you can see, it's very difficult to synchronize and visualize one ADSB frame. We have many signals, but it's very difficult to catch one ADSB frame. So we are going to see that the use of tags will be really helpful for us. For that, you have to introduce a new block, the correlate access code tag. The correlate access code tag is a block that will search for a pattern in the stream and attach a tag with a specific name on the next sample. For that, you need to indicate the access code, that is a pattern that you're looking for. The threshold is the numbers of error you accept in the access code, and the tag name. But now it's time to practice again. So I will let you read the exercise and we will meet up in a few minutes for the correction. Okay, let's go for a quick correction. Here we can find the access code 1010000101000000, etc. Up to the DF code. Simply copy and paste the access code in the correlate access code block. Threshold is 0, tag name is packet. Validate. In the properties of the timesync block, it's possible to set the trigger to tag, or you can let it to free and specify it later. First, you need the control panel. Then, specify trigger to tag and enter the tag name. Now you can adjust a little the visualization to see clearly the ADSB frame. It's really much better than before. Now we will go even further in the use of tags, and we will use a new block to save the data of each frames in separate files on the hard disk. For that, we will use the tagged file sync. To learn how it works, just read the wiki. A file sync that uses tags to save files. The sync uses a tag with a kburst to trigger the saving of a burst data to a new file. If the value of this tag is true, it will open a new file and start writing all incoming data to it. If the tag is false, it will close the file. So, we have to write a block that puts a tag burst with value true at the beginning of the frame and another tag burst with value false at the end of the frame. Next and latest exercise, I let you read and we will meet up in a few minutes. Okay, let's start by adding the tagged file sync block. And then we have to set the input type to byte. The GRC file provided contains a pre-completed Python block called ADSB divider. Open properties and open the code in editor. Use default. Okay. In the init, we will see that there is already a parameter which is a tag name, namely packet. Now we will complete the code in the work method. In the list of useful functions, let's get the one that allows you to retrieve the tags. Get tag in window. Copy and paste all the line in the editor. Tags equal self dot get tags in Windows. The input stream is 0. The start of window is 0. The end of window is the length of the input items, len input items 0. The tag name is packet. Here it's the parameter in self.tagname. Now we have to launch a for loop which will process all the tags. For in range len tags, a burst tag is added to each packet tag with the method addItemTag, with the output stream, the offset, the key, the value, and the source. Self.addItemTag, output stream 0, the offset of the tag, tags dot offset, the key is the name burst, pmt.intern burst. The value of this burst tag is true, so we write pmt.pmt_t. The name of the source is optional. The function will add a name by default. So we copy this line, pmt dot. We copy all this line. To add a second burst tag at the end of the frame, but the value false. It's necessary to specify the position of this tag. The packet tag was placed after the preamble on the DF code. If we want to recover all the frame, we must include the 5-bit DF code, so an offset of 10 or 11 samples for the first burst. The second burst, as we know that the message is 112 bits long, we add an offset of 224 samples. All we have to do now is save and check if everything is working. Okay, save. Now validate. We activate the block and connect it directly to the correlate access code block. Then to the time sync, and finally to the tagged file sync. Oh, it may have one or more errors. Let's look at the debug. It seems that we have an indentation problem. So let's go fix that in the code. maybe here. Okay. Here. And here. Okay, it looks good now. Look what happens when you execute the Flowgraph. Set the trigger to tag, indicate the name packet. Okay, it looks good. We see the burst tag with value true at the start of the frame and the burst tag with value false at the end. Well, let's take the opportunity to definitely adjust the time sync, set the trigger to tag, add a delay of 20 microseconds, and indicate the tag packet to trigger the stream. Okay, execute. Okay, everything works as expected. So, before finishing this tutorial, I offer you an interesting modification. So as not to have to enter the values of the offsets manually in the code, I think it's better to add two parameters, length and preamble, that the user can enter in the block directly in the GRC file. Okay, so open the code, open in editor. 11 is the preamble, so we'll name it self.preamble. Here too, self.preamble 224 is the length of the frame, so we will name it self.length. And the same principle as self.tag name, we add self.preamble equal preamble and self.length equal length. And finally, you add them in the init. Preamble equal 0 to initialize, length equal 0. We save the file and see if it works. Okay, we can indicate here the preamble and the length. Execute the Flowgraph. Okay, everything still works. But now let's see if the tagged file sync also works. Let's go in the home folder and we see a lot of files that are created continuously. Each size of file is 224 bytes, which is the expected size, because each value, 0 or 1, is stored on 1 byte here. Well, the tutorial is finished. Thank you for your attention. If you have any questions, you can join us in the chat or leave them in comments. In conclusion, and to wait until the chat resumes, here is a possible continuation of this part of the tutorial illustrated here. An external processing of the recorded files.
So this concludes the broadcast of the tutorial session of the European GNU Radio Days 2021. I hope you had as much fun watching this video and learning these new topics than we had recording them and training for this presentation. And now I must leave you because my setup for recording Sentinel-1, which is about to fly over Besançon in France, is ready, and I cannot wait for the satellite to join. Here is the Raspberry Pi getting ready to record the data stream from the B210 connected to the horn antenna, 5.405 gigahertz antenna. So I have to leave you, and have a good evening. Goodbye.